Now that we are done with the introductions, let's now start the first chapter, which is motion. So, we already know what motion means, right? You know that when a body is moving, it is said to be in motion, and when it stops moving, it is said to have come to rest. Now, later we will give a very correct and a more strict definition of motion, but for now, we can understand that movement means motion. Now, there are certain parameters we use to describe motion. In this session, we will talk about these parameters. So, let's understand this through an example. Let's say a particle starts from point A and then moves to a point B. Right. Additionally, say I tell you that the distance between A and B is 10 meters. Now, once again, I'm sure you already know this term, but let's define distance. So, distance is the first parameter that can be used to describe motion. Now, distance by definition is the length of path taken by the particle. Right. So in this diagram, you see that the line that I have drawn between points A and point B shows the path that the particle took to go from point A to point B. So if you measure the length of this path, it gives you the distance traveled. And that is the information given to you, that the distance traveled is 10 meters. So we can say that the length of this line, by the definition of distance, the length of this line is 10 meters, because that is what we must have measured to find that the distance is 10 meters. Right. So now the next thing which is used to describe motion is speed. Now say additionally I tell you that the time that the particle took to go from point A to point B was 5 seconds. Then the speed of a particle is basically the rate at which distance is covered. So let me first give you the formula. The speed is given by distance by the time taken to cover that distance. Now, you know that the distance is measured in meters, time is measured in seconds, so you can guess that the units for speed would be meter per second. So notice that we are talking about standard SI units, which we have already discussed. Distance is measured in meters and kilometers, right? But the SI unit is meters, and hence we are discussing the SI units, which is meter per second, right? So I've given you the formula, but let's understand speed. What essentially is being measured when we measure speed? So speed is distance by time. Like in this case, if you were to find speed, it would turn out to be 10 divided by 5, which is 2 meters per second. Right. So what does this number 2 signify? The speed of 2 meters per second. What does this tell you? It tells you that this particle is covering 2 meters in every second. That is why we say that speed is the rate at which distance is covered, because speed tells you the distance that will be covered in every second. Right. So the distance covered by a particle is the length of the path that it takes, and the speed of a particle, which basically gives you a measure of how much distance was being covered every second, is given by the formula distance by time, and its units are meter per second. Now these are the things that you have, I'm sure, learned in your elementary classes, right? So now, if you recall, we had said that whenever we do an analysis, generally we work with a coordinate axis. So let's draw a coordinate axis. You know that there will be an x-axis and a y-axis. So this is the x-axis and this is the y-axis. Now, point A gives you the initial position of the particle. Now, to measure this, taking the reference from the origin, we can draw a straight line from origin to point A. Now, this straight line gives you what is called the position vector. So, RA, what I've drawn here, shows you the position vector for A. So we usually use the symbol R to denote position vectors. So you would see that this symbol is used to denote position vectors, and the subscript A indicates that this is position vector of point A. Right. Similarly, I could write the position vector for point B by simply joining a line from origin up to point B, and this is the position vector B. Now, I must tell you this, if in case you have directly come to the first chapter, please go back and start from the introduction where we have discussed vectors and calculus. Right. So I'll be explaining this under the assumption that you are well versed with vectors. Right. So we had said that coordinate axis is used to take reference, which helps us measure or define positions. So when we use a vector to define the position of a point or a particle, it is called the position vector. So RA is the position vector of A, and similarly RB is the position vector for point B. Right. So far we have seen in this given situation that we can write two vectors to show the initial and the final position of this particle. Right. So let's now get back to the parameters we were talking about. We had understood distance and speed. The next parameter which is used to describe motion is called displacement. Now this is once again, I'm sure, something you already know about, but still, let's define displacement. Now, displacement is defined as the shortest distance between the initial and the final position of a particle. So, displacement is length of the shortest path between initial and final position. So, I'm sure you know that shortest path between any 2 points is the straight line joining those 2 points. And this is true whether those 2 points are in a plane. Well, any 2 points are in a plane, but that's a separate discussion, let's not get into it, but the shortest distance between any 2 points is always a straight line. So, in this case, if you want to find displacement, what you need to do is draw a straight line which joins point A with point B. So, this line gives you the displacement. To be very specific, the length of this line gives you the displacement. So, let me just give you a number, like let's say this length is 7 meters. In that case, the displacement of this particle when it goes from point A to point B is 7 meters. Right. And then displacement is a vector quantity. Right. So if displacement is a vector quantity, it would certainly have a direction. All right. That is what we learned, that scalars do not have a direction and vectors do have a direction. So I'm sure you figured it out that since I did not mention anything for speed and distance, these are scalar quantities. So speed and distance are scalar quantities. This is because they do not have a direction. In case of displacement, since it is a vector quantity, it has a direction. And displacement points from initial position. It points from initial position to final position. So if we talk about our example, in this case, the vector would point from A towards B. So this arrow which starts at A and ends at B, this gives us the displacement. If once again you recall, we had discussed that vectors are represented by arrows. So this particular arrow gives you displacement of this particle as it goes from point A to point B. So let me write it as a simple R. So this R, the vector R, represents the displacement of this particle. Right. Now since we have discussed vectors, once again, if you have not seen that part, please go back and revise that. So we had seen that from triangle rule, whenever there are two vectors placed such that the head of one is on the tail of the other, then we can add those vectors by triangle law. So looking at this figure, if you see RA and R are placed such that head of vector RA is at the tail of vector R, which means I can write that RA plus R should be equal to RB. Right? This comes straight from the triangle rule. Since the head is on the tail, the resultant vector will be from the tail of the first vector to the head of the second vector. If that is the case, I can write the displacement vector as the difference between RB and RA. Now if you think about it, RB is nothing but the final position vector and RA is the initial position vector. So the displacement of a particle can be given by the final position vector minus the initial position vector. Right. So since displacement is a vector, we have its description through vectors, which is given with the help of position vectors. Right. So displacement of a particle can be given by the final position vector minus the initial position vector. Right. Now moving on, we come to the fourth parameter which is used to describe motion, and it is velocity. Now, just as displacement is a vector counterpart for distance, velocity is the vector counterpart for speed. As we describe speed as distance by time, similarly, velocity is defined as displacement. It is defined as displacement divided by time. Now, once again, you know that displacement is measured in meters and time is measured in seconds. So the units for velocity are the same. So velocity is also measured in meters per second. Right. Now, velocity is once again a vector. So, to define velocity, the direction of velocity, let's look at its definition. We basically have displacement divided by time. Displacement is a vector and time is a scalar quantity. So their ratio will still be a vector quantity and it will point along displacement. So the direction of velocity will be denoted by V with an arrow on the top. The arrow on the top is a standard notation for vectors. So when I write this, I mean velocity. So I can say that velocity and displacement are in the same direction. So velocity of a particle will point in the same direction as the displacement of that particle. So let's understand that in our example, we had seen that the displacement is 7 meters. We also saw that the direction is in the direction of an arrow pointing from A towards B. Now to find the magnitude of velocity, we need to do displacement, which is 7 meters divided by time. So this gives you a value of 1.4 meters per second. So this is basically the velocity of this particle as it goes from A towards B. Right. Now, what about the direction? Since the displacement points from A towards B, velocity also points from A towards B. So this vector, which has magnitude 1.4, once again points from A towards B. Now there are a few details which are missing right now. We will fill these gaps when we discuss about average and instantaneous velocity. For now, let's understand velocity simply as displacement by time, whose direction is in the same direction as displacement. Right. And the final parameter that we will use to describe motion is acceleration. Now, once again, I'm sure you've heard and read about acceleration in your previous classes, but let's once again define it. So acceleration is again a vector, and it is defined as the change in velocity divided by the time taken. Right? So what acceleration measures is the rate at which speed changes. So it gives you the amount by which speed changes every second. So first of all, let's figure out its units. We see that it is a ratio of speed, or rather velocity, which is measured in meter per second, divided by time, which is in seconds again. So the units for acceleration are meter per second square. So acceleration is measured in meter per second square. Right. So if I give you a value of, let's say, 5 meter per second square, then what does this value tell us? It tells us that the particle is moving such that it changes its speed by 5 meter per second in every second. So I could say that if t equal to 1, that is the instance when time is 1 second, if the speed was, let's say, 15 meter per second, then when the time is 2 seconds, its speed will change by 5 meter per second and would become 20 meter per second. Right. So this is what the significance of velocity is. It tells you the amount by which speed, or rather velocity, changes in every second. Now the reason I'm using speed and velocity interchangeably is because in one-dimensional motion they are nearly the same thing. Right. We will get into the details of all these things as we go along. But for now, let's keep our definitions very simple. Right. So we understood distance is the length of path taken by the particle, speed is distance by time, and hence gives us the amount of distance covered in every second. Then we saw that displacement is the shortest distance between the initial and the final position, and velocity basically gives us the rate of change of displacement. Right. And finally, acceleration gives us the rate at which the velocity changes every second. Now, the acceleration is again a vector. So let's here very briefly discuss how we will see the direction of acceleration. Now, for any quantity, change is the final value minus the initial value. So, if I look at this vector A should be the final velocity minus the initial velocity divided by time. So time is a scalar and hence it will not affect the direction. So let's focus on the difference between the final velocity and the initial velocity. Now, an estimate of this can be taken by drawing a tangent to these points. So once again, we will discuss why I'm drawing a tangent. But I'm sure you can see it intuitively that at point A, the particle is moving in the direction that I've shown, right? If it moves along this curve, at this point, it must be going along this particular direction, right? Similarly, at B, you can guess that the velocity must be somewhere in the direction labeled, this direction that I've shown, right? So, to find the direction of acceleration, we must take the difference between these two vectors. So, we are interested in finding the direction of VB minus VA. So, how can we do that? If you recall, we had said that vectors can be translated parallel and then it makes no difference, right? So as long as I keep the length of this vector same and its direction the same, I can move it, right? So to estimate this direction, let me draw VA like this. And now VB can similarly be drawn like this. So this is vector VB and this is VA. What we wish to find is VB minus VA. To do that, let's draw the vector which is minus VA. So minus VA, you know, will point in this direction. So once we have this, we are basically looking for the sum of these two vectors, which is VB and minus VA. Now since their tails are joined, we will use the parallelogram law, and this is the resultant vector which gives us an estimate of the direction of acceleration. So as the particle moves from point A to point B, a rough estimate of its acceleration is this direction. Now, this is again something which you will understand better as we move along. The idea behind this discussion is to understand the fundamental parameters, these 5 parameters which are used to describe motion. And the idea of discussing this on this graph is that you should visualize these quantities, displacement, velocity and acceleration, as vectors, and it is very crucial that you understand that all of them have directions. And as we go along, it would get slightly more tricky figuring out the direction of these quantities, especially velocity and acceleration. Right. So let's now look at some very simple examples and understand them better. So let's say you're given that a particle moves along a square of side 10 meters. So let's label the square, let's call it A, B, C and D. So that's the name we've given to the 4 vertices. Now it is given that a particle starts from point A and it comes to point D via the paths A, B, C, D. Also, it is given that side of the square is 10 meters. And you know that the time taken to go from A to D, once again via the path ABCD, the time taken was, let's say, 15 seconds. In that case, we wish to find the distance covered, the displacement, the speed of the particle, velocity and the acceleration of the particle in this interval of 15 seconds while it goes from point A to point D via the path ABCD. Right. So let's start with the first part, which is asking for the distance covered. Right. So we know by definition that distance covered is the length of path taken by the particle. So first of all, you can see that the particle goes from A to B, B to C and then C to D. So the total length would be AB plus BC plus CD. Now since it is given that this quadrilateral is a square, we can say that all its sides are 10 meters. So the total distance would become 30 plus, 10 plus 10 plus 10, which is 30 meters. Right. So this was fairly easy. Let's now look at displacement. Now, displacement we had seen is the shortest distance between the initial and the final position. So the shortest distance between A and D is the line AD itself. And we had seen that the shortest distance between 2 points is a straight line joining these 2 points, right? So, for the second part, displacement is simply 10 meters. Now, displacement we know is a vector quantity, and we had discussed that this vector points from the initial position to the final position. So, the direction is from A to D. So this arrow with its tail at A and its head at D basically shows you the displacement. So this arrow AD is the vector representing displacement, right? So next comes speed. Speed we know as distance divided by time. So speed would be given by 30 divided by the time taken, which is 15 seconds, which gives you the value 2 meters per second. So this is the speed of this particle as it goes from A to D, right? Similarly, fourth part, the velocity is to be found. Velocity we know is equal to displacement by time. The displacement here is simply 10 meters, and so it would be 10 divided by 15, which if you simplify gives you 2 by 3, which is 0.66 meters per second. So this is the velocity of the particle as it goes from A to D. And finally, the last part is about acceleration. So now, before we come to acceleration, let's also look at the direction of velocity, since we know that velocity is a vector and hence we should look into where it points. Now, if you recall, we had discussed that velocity points in the direction of displacement. In this case, displacement points from A to D, and so does velocity. So velocity points along this arrow that we have already drawn, one which points from A towards D. Right. And finally, we come to acceleration. Acceleration we know is change in velocity by the time taken. Now, you may have noted that we are working under the assumption that the particle was moving with a constant speed. You will understand this further in the very next session when we will talk about average and instantaneous speed and velocity. Right. So we are here assuming that the particle maintains a constant speed, which is 2 meters per second. Right. So in that case, can we say that the acceleration is zero? It's not. It is because if you look closely, if I draw this square by dotted lines, let's try to see the direction of initial and the final velocity. The initial velocity obviously points in the direction from A to B. But when the particle goes from C to D, the velocity points in the opposite direction. So at point A, it was moving with 2 meters per second in this direction, whereas at point D, it is moving at 2 meters per second in the opposite direction. Now, if you remember in vectors, we had said that you must always have a reference direction, and that is why we draw the coordinate axis, or sometimes draw a single axis if the motion is one dimensional. So in this case, let's once again draw a coordinate axis, which basically means we are setting reference for directions as to which direction will be taken as positive. So if this is the x-axis, this is the y-axis, we could say that the initial velocity, now let's write it in strictly vector notation. Or maybe to start with, let's not go into the vectors. By going into vectors, I mean we are not yet introducing I cap and j cap. Let's simply say that the direction towards the right is taken as positive. Now, if that is the case, if we are taking this direction as positive, then we can say that the initial velocity, let me denote it by Vi, initial velocity, since it points in the direction which we are taking as positive, would be plus 2 meter per second. Similarly, the final velocity will be equal to, since it points in the direction opposite to the one we have taken as positive, the final velocity is minus 2 meter per second. Now, the change in velocity, delta V, will be equal to the final, which is minus 2, minus the initial, which is plus 2, which becomes minus 4. I hope you know this notation. Delta is used to represent change. So this triangle is a Greek symbol delta, and delta is generally used to denote change. So when I put delta before V, I mean the change in velocity, right? So delta V is given by minus 4 meter per second, and acceleration we know is delta V divided by time, which gives us minus 4 by 10, which means minus of 0.4 meter per second square. So the negative sign indicates that acceleration points in the direction opposite to the one we have taken as positive. So in this case, acceleration is in this direction and its magnitude is 0.4 meter per second. Right. Now let's solve the very same problem, but this time we'll initially assign our coordinate axis and then write everything in terms of vectors. Right. So let's say that we draw a coordinate axis such that the origin is at point D. So this is the x-axis, this is the y-axis, and the origin is at point D. If that is the case, we know that since distance is scalar, its value will not change. To find distance, we need to find the length of path, which is still the same and is equal to 30 meters. For the second part, to write displacement, we could say that displacement has to be the final position vector minus the initial position vector. Right? So, in this case, if D is the origin, what are the coordinates for point A? Think about it. Since A lies on the y-axis, its x coordinate is obviously 0. And its y coordinate, you can clearly see, is 10. So, the initial position vector, which is Ri, can be written as 0i cap plus 10j cap. I hope you understand this. We have discussed this in the chapter of vectors, that the coordinate x comma y can be written as xi cap plus yj cap. Right. So the initial position vector we have written as 0i cap plus 10j cap. What about the final position? The final position is D, which is origin itself. So that is 0i cap plus 0j cap. So the displacement vector turns out to be minus 10 j cap. Right? So the 10 gives you the value and the minus sign indicates that it is along the negative y-axis, which we already have seen is the case as displacement pointed from A towards D. Right. Similarly, to find velocity, we could simply do minus 10 j cap divided by the time, which was 15 seconds, and hence we obtain that velocity is the same value, which is 0.66 we had found. Yeah. So it is 0.66 meters per second, and it is minus j cap, the direction. Right. And finally, to find acceleration, what we could write is we could say that the final velocity, as we can see from this figure, this is what the coordinate axis looks like. So from here, the final velocity is minus 2I cap minus the initial velocity, which is plus 2I cap, divided by the time taken, which is given to be 15 seconds. So this becomes minus 4 by 15 I cap, which gives you the value that we have already found. I think we took the value of time as 10 seconds. This should have been 15. In the initial case, when we found acceleration, the value of time, we wrongfully substituted it as 10. It should have been 15. And your answer would hence be, you could calculate it yourself, simplify this fraction. So this is the value of acceleration. Right. So 4 by 15 gives you the magnitude, and this negative sign tells you that it points opposite to the direction in which plus x-axis points. Right. So this was a very simple example just to make the basics of motion clear to you. Now we will try to understand how and what is the difference between a measurement which is taken at a specific time instance and an instant and a measurement which is taken over an interval. Right. So in the next session, we will look at average and instantaneous speed.